Hello everyone, in this video I'm going to be explaining a past paper question I saw from a 2023, and this is a June CSEC paper. The main topic for this paper is, well, for this question is question 1, it's rates of reaction. So let's see how we can approach this question. Now the question says hydrogen peroxide, which is H2O2, decomposes to produce oxygen and water in the presence of potassium iodide at catalyst. So far we know some information. We know that hydrogen peroxide decompose mean that it broke down, right, to produce oxygen and water in the presence of potassium iodide catalyst. And already I'm just going to start to write my equation so I have an idea as to what is going on, my reactants versus my products. So I'm just going to write my equation, right? So it was H2O2, right, in the presence of a catalyst. Remember that if you have a reaction condition, you write it on top of the arrow. Catalyst would be like a condition. It breaks up, it decomposes to form oxygen and water. Okay, note that I'm not putting in any state symbols because I'm simply trying to have an idea as to what is going on in this reaction. Now it says the effect of concentration of the hydrogen peroxide on the rate of reaction was investigated. What they're saying is that they're testing to see how the concentration of our reactant, so this is our reactant here, how its concentration affects the rate of the reaction, right? Now it says for each experiment the concentration of hydrogen peroxide was changed. So they said that they changed the concentration, and that would make sense, right? If you're trying to see how concentration affects the rate, of course you would have to change the concentration at different intervals, right? And why I say this is because sometimes you have to design your experiment to test how different things affect the rate of a reaction. And I don't want to diverge too much, but if you're testing to see how concentration affects the rate, you simply change the concentration at different time intervals. If you're testing to see how temperature affects the rate, you can simply change the temperature, right? Continuing, yes, so it was changed, and the time taken, let me see if I can find my pen, right, my pointer, and the time taken for the hydrogen peroxide to decompose was measured using a stop clock shown in figure 1, right? So let us see the time that we have here. Okay, so for experiment 1, this time right here, it goes from 55 to 60. So every stroke that we see, we call these graduated marks, but every stroke that you see here represents 1, and that would make sense. So if this is 55, then this is 56, 57, 58, 59, 60, right? So this one right here, we're gonna say it is 59. So this is 59. And you know, they did not tell us how it's measured, if it's seconds or minutes, but I think it's gonna be said in further down. For experiment 2, it goes 40, 41, 42. And as I do this, I encourage you to also try to attempt the question. I would have shared this in the WhatsApp group already, so you can just look at this to help answer the question. Number 3, it's at 31, right? 30, 31. Number 4, this is 25. And number 5 is 21. Okay, so let's move on. I believe we would have a table to complete next. Yes, and let me just fill it in. It was 59, 42, 31. and then we had 25, 21. Now, when we're calculating the rate, sometimes you calculate the rate using this way, which is the inverse of time, and I'm going to write that. Inverse of time, which means 1 divided by time. So it's time inverse. Other times, of course, you can calculate rate using change in volume or change in concentration divided by time, change in time. Alright, so let us calculate this. So it's 1 divided by the time. So I'm going to do 1 divided by 59, and I get 0.0169. 1 divided by 42, I get 0.0238. 1 divided by 31 equal 0.0323. 1 divided by 25, 0.0400. And 1 divided by 21, 0.0476. So that's just 5 marks. 5 marks to complete our table. Alright, let us move on. So it says complete the table, and guys, please to try to read the questions at the bottom. Sometimes we miss those and we lose marks. It says complete the table by calculating the rate of reaction 1 divided by time to 3 decimal places. Alright, so, and this is why it's important, because I would have written my answers in 4 decimal places, which is about I'm going to say this is 3 significant figure, but since it is 3 decimal places, let me just make this adjustment here. So this would now be 0.0169 rounded up. It's gonna be 0.017, 0.023 becomes 0.024, 0.0323 becomes, well, I can just erase this 3 here, can erase that one, and this is just 8 here. Alright, yes, let us move on. Using the axis, so that's 10 marks, 10 marks just to fill out the table. Nice. Using the axes provided in figure 2 on page 7, plot a graph of rate of reaction versus concentration of hydrogen peroxide. So usually, whatever they say first in your statement, that would go on the y-axis, right? So whatever they say first in the statement goes on the y-axis, and whatever comes next would go on your x-axis, unless they say otherwise, of course. So it would be rate of reaction on the y-axis and concentration of hydrogen peroxide going on the x-axis, right? And they also say to draw the line of best fit through the points, which means that we need to draw a straight line through as many points as possible. All right. So yeah, I'm gonna look at the graph here. Note that for this graph, they have a lot of information present, and usually you're not given this much information, but I'm happy that they gave it to you so you know how to do your graphs on your own. So whenever you're doing a graph, right, of course it is important that you indicate what your lines mean, or whatever the points, what units you're using. So for example, over here they have 0.010, they jump 2 centimeters, and then they have 0.015, right, and so on and so forth. So you need to have your numbers written on your graph. All right, now next, of course, you need to ensure that you have the unit, or you're labeling your axis with the unit, right? So you can't just have the unit alone. You have to make sure that you label the axis with the unit. That is important. So in this case, they put rate of the reaction, and I would prefer for you, well, this is actually better. Yes. So it's rate of the reaction, and they put the unit. You can often find the unit on your table. It's there. And the unit here is s to the -1. This means inverse of seconds, or inverse of time. Yes. And then on our x-axis, as we can see here, they're very specific. They don't just tell us hydrogen peroxide, they tell us what about hydrogen peroxide. They say concentration of hydrogen peroxide, and they put the unit, which is mole per dm cube, right? So you have to include the title for each of your axes. Another thing that they did was that they gave us, of course, the title. This is important. Know that they did not just say rate of reaction versus concentration. Know that their title is very specific. And this is how we mark your labs as well. We're looking for how specific and how descriptive you are. You can't just say 21, right? You have to say 21 dumpling. You have to tell us what is going on. It doesn't have to be long, of course, but you just have to be specific. So in this case, it says figure 2, and it is graph of, right? It's not diagram of, it is graph of, because of course this is a graph. If it was a diagram, then you would say diagram of. If it was a drawing, you would say drawing showing or drawing of, right? You have to be specific. We have to know what's going on. Yes, suppose I could not see, right? So you have to be descriptive. Or what if there were no questions following? Yes, so being descriptive is key. So it says graph of rate of reaction versus concentration. Once again, they're being specific. Concentration of hydrogen peroxide, H2O2, right? And sometimes you can also put this on your graph itself at the top. It will go somewhere here, and you put it in all caps, right? So we have a lot of key things. The only thing that we're missing, of course, is the scale, right? And we're going to write the scale at the end once we've seen the space that we have left. All right, so let us plot. I'm going to see if I can take a screenshot of this so I can have it. So this is rates. This is rates, and I did not get the concentration. So it goes from 0 . Okay, awesome. All right, so that's rate, and this is concentration. Now, whenever you're drawing a graph and you're going to put your points on the graph, somebody would have asked for this in a previous video, right? And you're going to put the points on the graph. I want you to practice drawing your points 2 ways, right? So you either use the cross and you circle that cross. Why we do this is because sometimes there's some error in the lab, and this circle kind of shows us, it gives us a little estimate around to show us that, hey, the lab isn't perfect, right? When you have the cross alone, you're saying that, oh, my lab was free of errors, nothing incorrect happened, right? So whenever you do it, you can use the cross and the circle, or you can use the X and the circle. I see sometimes persons using dot and circle, but this one is my preferred way of going. I use the cross and the circle. It's easier for me because I'm able to see my X, the lines on my X and the lines on my Y very clearly. It's not that difficult. All right, so let us plot our graph. So the first one we're gonna do is 0.10 for concentration to 0.017 for rate. 0.010. So right here, it would be around right here for concentration, and the rate is 0.017. All right, so looking at the rate, this one at the x-axis, it goes up every 2 centimeter. We're going up by 0.05, right? Every 2 centimeter, we're going up by 0.05. How I knew it was 2 centimeter? From here to here is 1 centimeter, and from here to here is another centimeter. So every time we move by 2 centimeters, we're going up by 0.05 mole per dm cube. That's for the x-axis. For the y-axis, it's the same, however the unit is different. Every time we go up by 2 centimeters, we are going up by 0.005 inverse of time. Right, that is very important. It's not just 0.05, it is 0.005 inverse of time. All right, so I need to find where 0.017 would be. Now, if this, how I'm gonna do it, I'm gonna use my half method. If this is 0.005 and this is 0.010, halfway between these two values is gonna be 0.075, right? Yes, that would be 0.075, and we're counting by twos for each. So here would be 0.006, 0.007, 0.008, 0.009, and then 0.010. Okay, so I believe we can find 0.017 easily. So it's gonna be, this is 0.015. So therefore, if we go 1, 2, this is 0.017, 1, 6, sorry, and then this is 0.017 right here. If I bring it over to the 0 point, so my point would just be about right here. And guys, bear with me, this is my first time plotting a graph using this method. Trying my best here. All right, I think I lost it. It would be here. Right, notice how I said my stick method kind of works for me, my cross method. So it goes directly on my x-axis, indicating where the 0.017 is, and then on my my y-axis 0.017 and my x-axis 0.010. Right, so that's our first point down. Next one, concentration is 0.015, which is here, and then the rate is 0.024. So 0.024 is just about, if this is 0.025, then if I take away 2 of these, then I would get 0.024. And we can do it this way, of course. So it is 0.02, so that's 20, then this is 21, 22, 23, 24. I'm trying my best to get it to be as easy for you as possible so you understand. All right, so we're finished with the second one. The third one, 0.20, and then the rate is 0.032. So if this is 30, then this is 31, and then this right here is 32. So I'm gonna 1, 2, and then we're almost finished. The next one is 40, 0.25 to 40. Alright, this one is easy to find. 40 is right here. That's where 40 is. And then I believe the next one is 48. I hope that is 40, and I don't remember if it is 40. It looks like 46. Actually, it is 40, yes. Alright, 48. So if this is 45, it's 45, 46, 47, 48. It's just about there. I feel like that one isn't correct. 5, 6. Yeah, that one is not correct actually. So it is 4, 5, 6, 7, 8. Yes. Yeah, it would have been correct initially. Alright, so we have our points and we can see a clear straight line. I believe we're finished. We did all 5. We can see a clear straight line for this graph. I'm gonna get my ruler. I'm gonna try to angle it. Look at that, perfect. Nice. It doesn't have to go through all the points. It goes through most of the points, right? It's almost like an average. It goes through most. And then I draw my line. This is gonna be a tricky one. I have never used the ruler here before. Alright, let me hope I can. Whew. Nice. Alright, not bad. Yes, so that's our line of best fit. I need to put in my scale. So how I do my scale? So I do y-axis. Y-axis was y-axis, x-axis, and everyone is taught differently, of course, but this is how I do mine. Right, so the y-axis, it was 2 centimeters for both, and on the y-axis we were moving up by 0.005. The unit is inverse of time, so it's s to the negative 1. And on the x-axis we were moving up by 0.05, and this was mole per dm cube. Right, so everything is complete for our graph. And when we look at the graph, we can see that as we increase the concentration, notice as we go this way, we're increasing the concentration, right? As we go to the right, the concentration is increasing. It goes from 0.05 to 0.40. 0.40 is, of course, bigger than 0.05. Right, so we're increasing the concentration going this way, and this way from here we're increasing the rate, right? So what we can see that this is very much, it's directly proportional. The concentration of the hydrogen peroxide is directly proportional to the rate of reaction, which means that as we increase the rate of reaction, or as we increase the concentration of hydrogen peroxide, the rate of the reaction would of course increase, right? So really that means that as we're adding more reactants, we're increasing how fast the reactants would react to form the products, which were oxygen and hydrogen, well, water, oxygen and water, right? So that's what it means. So we did our graph. That should be another, that's 5 marks. We're not supposed to spend too long on it because it's just 5 marks. It's a good 5 marks, but try not to spend too much time on it, Right, now we're at some questions, we're at some definitions. It says define the term rate of the reaction. The rate of reaction, as it says rate and it says reaction, you can use that to make your definition. So rate, it's the speed at which reactants, because you know that a reaction has reactants and products, right? So it's the speed at which the reactants convert to products. It's how fast the reactants convert to products, or it's the speed at which a chemical reaction occurs. That still means that it's how fast the reactants convert to products. Now we can also use this one here. This actually ties in with the way we calculate rate of reaction. It says it's the change in concentration of reactants or products per unit time. Rate deals with time, of course, so this would make sense. It's a change in concentration of reactants or products per unit time. So any of those definitions could, of course, give you 1 mark. Now we have another definition. It says define the term catalyst, right? And I know 3 things about a catalyst, and I want you guys to put this in a sentence for me. Right, so 3 things that I know about a catalyst. For one, a catalyst, it speeds up a reaction, right? So it speeds up a reaction. 2, a catalyst does not get used up. So if you start off with the catalyst, you should end up back with the catalyst at the end of the reaction. So it does not get used up. And the next one is that it, oh, I know 4 things actually. It increases, oh yeah, it would have been there already. It lowers the activation energy. Or we could say that a catalyst provides an alternate pathway for a reaction. So we know 4 things. Right, why I say this, and I'm just going to diverge a little bit. If you remember your graph, that looks like this. Right, how the catalyst works, of course, you know that from here where you have your reaction, your reactants, the top part of the hill, that's your activation energy. It's the amount of energy that a reaction needs to proceed, right? Now the catalyst works, it speeds up the reaction by, of course, providing an alternative pathway for the reaction to occur by lowering your activation energy. So of course this would be the original activation energy, but once you add the catalyst, it lowers the activation energy and you still produce the same products. You know, let me write reactants and products. You still produce the same amount of products, however you just produce those products at a faster time. That's what the activation, that's what the catalyst does. It just changes how fast the reaction proceeds by simply lowering the activation energy. And you could put that into words for me, exactly what I just said. You can replay it. Yes, so that would be our definition. Let me try and write it. It's gonna take me some time, so bear with me. So it is a chemical substance that speeds up a chemical reaction by lowering the activation energy of the reactants. And of course you can definitely make your own definition from all the points I just gave you. Right, these are all valid information, and they are also common in multiple choice questions. Right, so let us move on. All right, I think we completed about not good portion. Yes. So it says, using your graph, describe the relationship between the rate of the reaction and the concentration of the hydrogen peroxide. I would have said this earlier. As the rate of the reaction, well, as the hydrogen peroxide increases, the rate of reaction would also increase. That's all you're doing. You're saying how they relate to each other. So as the concentration of the hydrogen peroxide increase, the rate of reaction also increases. 2 marks just for analysis. They like to give marks for how you can analyze certain things. Now the next question says, determine the concentration of hydrogen peroxide given that the rate of reaction is 0.045 inverse of time, right, or s to the -1. So this, we're gonna be using the graph to find this value, right? All we're gonna do is that we're gonna find the rate on the graph and then try to find the concentration that it aligns with. So it's 0.045 s. Right, so we're going to look for this value on our rate portion of the axis of the graph. Right, 0.045, it is here. That's it. And what we do is that we're going to extrapolate to where we have our straight line. Extrapolate meaning that we're making some dashed lines going straight to where our straight line is. If it is a curve, you would do the same thing. You would extrapolate to where the curve is, right? And then, since we need to find the concentration, we're going to extrapolate down to where the concentration is. So I'm going down. I think it is midway here. And of course, this would vary based on everyone's graph, but as long as you're able to use your graph correctly, you would of course get your mark. Alright, so our concentration is, so that's 0.252678. So 0.285. That's the answer that I get based on my graph. Why I say 285 is because it's between, it's right here. So right there is 8, and it's kind of a little bit, it wouldn't be 285, you know. It would not be 285. So it's right here. That's 285. I'm gonna say it's about 283, so it's right here. All right, I need to finish this video before my battery dies. So it's about right there, so 0.283. Units mole per dm cube, because we're looking for concentration. Calculate the mass of hydrogen peroxide present in the concentration identified in EII. Right, so we need to calculate mass. How much marks is this? 1 mark.